So here's something worth thinking about as you settle in tonight. Right now, wherever you are, whatever time your clock says, that number, that specific hour and minute, is a human invention. Not the moment itself, obviously. The moment is real. The earth is really spinning. The stars are really moving. Your body is really doing its slow, quiet work of breathing and resting. But the way we chop all of that up into hours and minutes and seconds, the way we agree that it's, say, 11:47 at night, that whole system is something people had to figure out, argue about, get wrong, fix, argue about again, and then slowly, painstakingly stitch together across centuries. And the story of how that happened is one of the most fascinating, tangled, quietly dramatic stories in all of engineering and science. So let's just talk about it. No rush. Let's start at the very beginning, and I mean the very beginning, and just see where it takes us. The first thing humans ever noticed about time was the obvious stuff. The sun comes up, the sun goes down. That's a day. The moon swells into a bright circle, then thins away to nothing, then comes back. That's roughly a month. The weather warms, the crops grow, the leaves fall, the cold comes, and then it all starts over. That's a year. These cycles were so reliable, so woven into daily survival, that every civilization on Earth locked onto them independently. You didn't need a clock to know these rhythms. Your body already knew. Your stomach knew. The birds knew. The river knew. But here's the thing, and this is where it starts getting interesting, even at this very early stage. None of those natural cycles divide neatly into each other. A lunar month isn't exactly 30 days. It's about 29 and a half, and 12 lunar months don't add up to a solar year. They fall short by about 11 days. So right from the start, the moment anyone tried to build a calendar, tried to write down a system that would tell you when to plant, when to harvest, when the river would flood, they ran into a mismatch. Nature doesn't do clean math. The cycles are close to lining up, tantalizingly close, but they don't. And that gap, that annoying little remainder, has been driving people slightly crazy for at least 5,000 years. The ancient Egyptians are a wonderful place to start because they had a very specific, very practical reason to care about this. The Nile flooded every year, and that flood was everything to them. It deposited rich, dark silt across the farmland, and without it, Egypt was just desert. So knowing when the flood was coming wasn't an intellectual exercise, it was survival. And they noticed something beautiful. Just before the flood, right around late June by our modern reckoning, a particular star appeared on the horizon just before sunrise. That star was Sirius, the brightest star in the night sky, and its reappearance after being hidden for about 70 days became their signal. They called this event the heliacal rising of Sirius, and they built their calendar around it. The Egyptian civil calendar had 365 days, divided into 12 months of 30 days each, plus 5 extra days tacked on at the end. They called those the epagamenal days, which is a wonderful word. And for its time, this was remarkably clean and practical. But here's the catch, and you might already see it coming. The actual solar year isn't exactly 365 days. It's about 365 and a quarter. So every year, the Egyptian calendar drifted by about a quarter of a day relative to the actual seasons. That doesn't sound like much, right? But after 4 years, you're off by a full day. After 40 years, you're off by 10 days. After centuries, the calendar and the seasons are completely out of sync. Your summer month is happening in winter. Your flood season marker is meaningless. The Egyptians knew about this drift. They tracked it, but for a long time, they just lived with it. The calendar cycled all the way around and came back into alignment every 1460 years or so, a period they called the Sothic cycle. There's something almost poetic about that, an entire civilization watching their calendar slowly slide out of phase with reality, knowing it would eventually come back, just not in anyone's lifetime. Now, meanwhile, over in Mesopotamia, modern-day Iraq, the Babylonians were taking a completely different approach, and they gave us something we still use every single day. The Babylonians were obsessed with the number 60. Their entire number system was base 60, which is called sexagesimal. And if you've ever wondered why there are 60 minutes in an hour and 60 seconds in a minute, and why a circle has 360 degrees, this is why. It all traces back to Babylon, roughly 2,000 years before the Common Era, maybe earlier. And here's what's clever about 60. It's divisible by a huge number of smaller numbers: 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30. That makes it incredibly flexible for dividing things up. If you want to split an hour into halves, thirds, quarters, fifths, sixths, tenths, twelfths, 60 handles all of those cleanly, no messy fractions. Try doing that with 10. 10 divides evenly by 1, 2, 5, and 10. That's it. 60 is just a much more cooperative number when you're trying to carve time into usable pieces. The Babylonians may not have thought about it in exactly those terms, but the practical result was a system so useful that it survived the fall of Babylon, survived the Greeks, survived the Romans, survived the Middle Ages, survived the invention of digital computers, and is still sitting right there on your phone's clock display tonight. 4,000 years, give or take. That's a pretty good run for any piece of engineering. The Babylonians were also extraordinary astronomers. They kept meticulous records of celestial events, eclipses, planetary movements, the positions of stars, on clay tablets, thousands of which have survived. And from those records, they developed mathematical models to predict when things would happen in the sky. Not perfect predictions, but impressively good ones. They could tell you when the next lunar eclipse would occur, sometimes years in advance. And the reason this matters for our story is that astronomy and timekeeping were, for most of human history, the same discipline. You couldn't do one without the other. The sky was the clock. Let's talk about sundials for a moment, because they're deceptively interesting. The basic idea is simple. Stick something upright in the ground, watch where its shadow falls, and you can track the sun's movement across the sky. The Egyptians used obelisks this way as early as 3,500 years ago. But a shadow on the ground isn't the same thing as a clock, not really. The shadow moves at different speeds depending on the time of year, because the sun's path across the sky changes with the seasons. In summer, when the sun is high, shadows are short and move quickly. In winter, when the sun is low, shadows are long and move differently. So the hours you read off a simple sundial aren't equal in length. A summer hour is different from a winter hour. These are called temporal hours, or unequal hours. And for most of the ancient world, that was just how time worked. An hour wasn't a fixed thing. It stretched and compressed with the seasons. Think about what that means for a second. If you lived in ancient Rome and someone said, "Meet me at the third hour," that appointment was at a different clock time in July than in December. The day, meaning the period of sunlight, was always divided into 12 hours, and the night was always 12 hours. But since days are longer in summer and shorter in winter, Those hours expanded and contracted accordingly. We're so used to fixed, equal hours that this feels bizarre, but it was the norm for thousands of years. And honestly, it made a certain kind of sense. If your life revolved around sunlight, when to work, when to eat, when to sleep, then dividing the sunlight into equal portions, whatever their absolute length, was perfectly practical. The Greeks refined sundial design considerably. There's a beautiful device called the Tower of the Winds in Athens, built around 50 BCE, which is essentially an octagonal marble tower with sundials on each face, oriented to catch the sun from different directions. It may have also contained a water clock inside, which brings us to the other great ancient timekeeping technology, clepsydra, or water clocks. The idea behind a water clock is straightforward. You have a container with a small hole near the bottom, and water drips out at a more or less steady rate. You can mark the water level on the inside of the container, and as the level drops, it passes each mark, telling you how much time has elapsed. Or you can do it the other way. Let water drip into an empty vessel and watch the level rise. Either way, you've got a clock that works at night, works on cloudy days, works indoors. It doesn't need the sun at all. The Egyptians had water clocks at least by 1400 BCE, and there's a particularly lovely one from the reign of Amenhotep III that's shaped like a truncated cone, wider at the top, narrower at the bottom. And that shape isn't decorative, it's engineering. See, if you have a straight-sided cylinder with a hole in the bottom, the water drains faster when the container is full because there's more water pressure pushing down, and slower as the level drops. So the drip rate isn't constant, which means your time markings would be unevenly spaced. But if you taper the container, make it wider at the top where the pressure is high, and narrower at the bottom where the pressure is low, you can partially compensate for this effect. The wider upper section holds more water, so even though it's draining faster, the level drops at a more uniform rate. It's not perfect, but it's a genuinely clever piece of fluid dynamics worked out empirically, without calculus, without formal physics, just by careful observation and iteration. Someone sat there, watched water drip, noticed the problem, and shaped the vessel to fix it. That's engineering at its most fundamental. The Greeks and Romans used water clocks extensively, especially in legal and military contexts. In Athenian courts, speakers were given a fixed amount of time to make their arguments, measured by a water clock. When the water ran out, you were done. There's actually a phrase in ancient Greek legal language, "My water is being used up," meaning my time is running out. Roman legions used water clocks to time the changing of the guard during night watches, and Ctesibius of Alexandria, working around 270 BCE, built what might be the most sophisticated water clock of the ancient world. He used a constant flow mechanism, essentially a regulated supply that kept the water level in the main chamber steady, so the outflow rate was truly constant. The rising water in a receiving vessel lifted a float, which was connected to a pointer that indicated the time on a cylindrical dial. And here's the really impressive part. The dial was designed to rotate slowly over the course of the year, so the hour markings shifted to account for those unequal seasonal hours we talked about. It was, in a real sense, an analog computer for time. But all of these devices, sundials, water clocks, even the astronomical observations of the Babylonians, shared a fundamental limitation. They couldn't keep time with any real precision over long periods. Water clocks were affected by temperature, because cold water is more viscous and flows slower. Sundials were useless at night and in bad weather. and none of them could tell you anything about time at a resolution finer than maybe a quarter of an hour on a good day. For the ancient world, that was fine. Nobody needed to know the time to the minute, let alone the second. Life moved at the pace of sunlight and seasons, and approximate time was good enough. But something was about to change, slowly at first, and then with gathering momentum. And the force that would drive the need for better timekeeping wasn't science, and it wasn't commerce, at least not initially. It was religion. Specifically, it was Christian monasticism and the rigid schedule of daily prayers that monks were expected to observe. The Rule of Saint Benedict, written around 530 CE, prescribed specific times for prayer throughout the day and night, the canonical hours. Matins in the deep night, lauds at dawn, prime at the first hour, and so on through the day to compline at bedtime. These weren't suggestions, they were obligations, and getting them right mattered, which meant that monasteries needed some way to know what time it was, reliably, even in the dark, even in winter, even when the sky was overcast for days on end. And it was in the monasteries of medieval Europe, in those quiet stone buildings where the days were measured out in prayer, that the mechanical clock was born. And what a strange, magnificent invention it turned out to be. Because here's the thing. The first, mechanical clocks didn't have faces, they didn't have hands, they didn't display the time at all. They rang bells. That's it. The word clock itself comes from the medieval Latin clocca, which just means bell. These earliest devices were alarm mechanisms, essentially, machines designed to wake a monk at the right hour so he could rouse the others for prayer. Before that, the poor soul assigned to keep watch through the night had to rely on burning candles marked with lines, or counting psalms, or watching the stars through a window and hope he didn't doze off and miss matins. So the mechanical clock wasn't invented to tell time in the way we think of it. It was invented to ring a bell at the right moment. And the engineering challenge behind that. How do you build a machine that can measure the passage of time using only gears and gravity? That challenge would reshape the entire world. Now, let's talk about how these early clocks actually worked, because it's a beautiful piece of engineering. And once you understand the core idea, everything that comes after makes so much more sense. The fundamental problem is this. You need something that moves at a constant, predictable rate. With a water clock, that something was flowing water. With a sundial, it was the apparent motion of the sun. But a mechanical clock needs a mechanical source of steady motion, and in medieval Europe, the solution they arrived at was a device called the verge and foliot escapement. That's a mouthful, but the idea is actually pretty intuitive once you picture it. Imagine you have a weight hanging from a rope that's wound around a drum. Gravity pulls the weight down, the rope unwinds, the drum turns, and that turning motion drives a series of gears. Simple enough. But here's the problem. If you just let the weight fall, it'll drop as fast as gravity allows, the drum will spin freely, and all your gears will whip around in a second or two. That's not a clock. That's just a falling weight. What you need is something that lets the weight descend slowly, in controlled little steps. You need a way to release the energy bit by bit, tick by tick. And that's what the escapement does. It's the heart of the mechanical clock, the thing that makes it a clock instead of just a gear train. The verge escapement uses a vertical shaft, the verge, with two small paddles called pallets sticking out near the top, set at roughly 90 degrees to each other. These pallets interact with a toothed wheel called the crown wheel, which is being driven by the falling weight. As the crown wheel tries to turn, one of the pallets catches a tooth and stops it. But the momentum of the catch pushes the verge, which rotates, swinging the foliot. That's a horizontal bar balanced on top of the verge, sometimes with small adjustable weights on it. As the foliot swings one way, the first pallet releases the crown wheel tooth, but then the second pallet catches the next tooth on the other side, and so the wheel advances by exactly one tooth. Then the foliot swings back, the second pallet releases, the first one catches again, and the wheel advances another tooth. Back and forth, tick and tock, each swing letting the weight drop just a tiny bit further. Think about what that means. The foliot swinging back and forth is the time-keeping element. Each swing takes roughly the same amount of time, and each swing allows the gear train to advance by one precise increment. The falling weight provides the energy, but the escapement controls how fast that energy is released. It's a governor, a regulator, and the beauty of it is that it's entirely mechanical. No water, no fire, no sunlight, just gravity, metal, and ingenuity. Now, I should be honest with you. These early virgin foliot clocks were not very accurate. They could drift by as much as 15 minutes a day, sometimes more. The foliot doesn't have a natural period the way a pendulum does. Its swing rate depends on friction, on how much force the crown wheel is exerting, on temperature affecting the metal, on wear in the bearings. By modern standards, they were terrible clocks. But by medieval standards, they were miraculous. For the first time in human history, you had a machine that could run day and night, rain or shine, summer or winter, ticking away in a bell tower, and it only needed someone to wind the weight back up once or twice a day. That was revolutionary. The earliest references to mechanical clocks in Europe start appearing in the late 13th century. There's a record of a clock being installed at Dunstable Priory in England in 1283. Another at Exeter Cathedral around the same time. By the early 1300s, they were spreading across Europe. Cathedrals, monasteries, town halls, and here's where something really interesting happens, something that goes beyond just engineering. These clocks started to change how entire communities related to time. Before the mechanical clock, time in a town was local and approximate. The church bells rang when the monks decided it was time, based on their best guess from whatever timekeeping method they had. Different towns, different schedules. But once you had a mechanical clock in the town square, suddenly everyone in that town was synchronized. The clock became a public utility, a shared reference point. Merchants could agree to meet at a specific hour. Markets could open and close on schedule. Workers could be expected to start and stop at defined times. The mechanical clock didn't just measure time. It created a new kind of social time, a shared, public, standardized time that everyone in earshot of the bell could agree on. And this is where commerce starts to enter the picture. In the textile towns of Flanders and northern Italy during the 13 and 1400s, work bells, sometimes separate from church bells, began regulating the working day. There are records of disputes, even riots, over who controlled the town clock, because controlling the clock meant controlling the rhythm of labor. If you could make the work bell ring later in the evening, you got more hours out of your workers. The clock, this device born in monasteries for the purpose of prayer, became an instrument of economic power. It's one of those twists in the history of technology that feels almost too neat to be true, but there it is. Now, let's talk about the people who built these clocks, because the craft of clockmaking in the medieval period is fascinating. The earliest clock builders were often blacksmiths or locksmiths, people who already worked with iron and understood gears and mechanisms. But as clocks grew more ambitious, a specialized guild of clockmakers began to emerge, And some of them were extraordinary. Take Giovanni da Dondi, an Italian physician and clockmaker who, between 1348 and 1364, built what's known as the astrarium. This wasn't just a clock, it was an astronomical masterpiece, a device with 7 faces showing the positions of the sun, moon, and all 5 known planets, plus a perpetual calendar, nodes of the moon's orbit, and the times of movable feasts. Da Dondi spent 16 years on it, and he left behind incredibly detailed manuscripts describing every gear, every ratio, every component. When modern horologists have reconstructed it from his notes, they've found it to be a work of staggering precision and ingenuity for its era. The man was obsessed in the best possible way. He solved problems that wouldn't be addressed again for centuries. But da Dondi's astrarium, magnificent as it was, still used the verge and foliate escapement, which meant it still had that fundamental accuracy problem. And for most of the medieval period, nobody could figure out how to do much better. Clocks got bigger, more elaborate, more beautiful. The astronomical clock in Strasbourg Cathedral, first built in the 1350s and rebuilt in the 1570s, is a towering masterpiece of art and engineering. But the underlying timekeeping mechanism remained essentially the same for about 300 years. The verge and foliate was good enough for bells and astronomical displays, but it couldn't give you precision. And as long as nobody needed precision, that was fine. But the world was changing. By the 15 and 1600s, European navigators were sailing farther and farther from home, crossing open oceans where you couldn't see land for weeks. And they had a problem, a deadly, urgent, enormously expensive problem that would eventually transform clockmaking from a craft into a science. The problem was longitude. Here's the issue, and it's worth taking a moment to really understand it, because it connects timekeeping to navigation in a way that's both elegant and, when you think about it, kind of obvious. If you're at sea and you want to know how far north or south you are, your latitude. That's relatively straightforward. You measure the angle of the sun at noon, or the angle of the North Star at night, and with some simple tables, you can figure out your latitude to within a degree or so. Sailors had been doing this for centuries, but longitude, how far east or west you are, that's a completely different problem. There's no fixed star that tells you your east-west position. The sky looks essentially the same, whether you're in the mid-Atlantic or off the coast of Portugal, at least in terms of what's directly overhead at any given local time. But here's the key insight, and people understood this as far back as the early 1500s. The Earth rotates 360 degrees in 24 hours, which means it rotates 15 degrees every hour. So if you know what time it is right now where you are, local time, which you can determine from the sun, and you also know what time it is right now at some reference location, say your home port, then the difference between those two times tells you how far east or west you've traveled. 1 hour of difference equals 15 degrees of longitude, 2 hours, 30 degrees, and so on. Think about what that means. If you had a clock, a really, really good clock, that you set to your home port's time before you sailed, and that clock kept perfect time throughout your entire voyage, across weeks or months at sea, through storms and salt spray and temperature swings, you could compare it to local noon every day and know exactly where you were on the globe. The problem of longitude was, at its heart, a problem of timekeeping. And in the 16 and 1700s, no clock on Earth was good enough to solve it. The verge and foliate mechanism, even in its most refined forms, drifted far too much. A clock that lost just 1 minute a day would, after a month at sea, put you off by nearly half a degree of longitude. which at the equator is about 30 nautical miles, enough to miss your destination entirely, or worse, to run aground on rocks you thought were nowhere near you. Ships were lost, thousands of sailors died, fortunes vanished beneath the waves, and the search for a solution would produce one of the most remarkable stories in the entire history of engineering. A story about a self-taught carpenter's son from Yorkshire who would spend his entire adult life building clocks that nobody believed were possible. But before we get to John Harrison and his extraordinary marine chronometers, we need to talk about the invention that made precision timekeeping thinkable in the first place. An invention that came not from a clockmaker, but from a man lying in bed watching a chandelier swing in a cathedral. And that man was Galileo Galilei. And the year was around 1583, though the exact date is a bit fuzzy. Some historians put it a year or two earlier, some a year or two later. Galileo was young, maybe 19 or 20, a medical student at the University of Pisa, and the story goes that he was sitting in the Cathedral of Pisa during a service, probably not paying as much attention to the sermon as he should have been. And up above, a lamp, a large hanging oil lamp, or chandelier depending on which version you read, was swaying gently. Maybe a draft caught it. Maybe someone had pulled it aside to light it and let it go. Whatever set it moving, Galileo watched it swing back and forth, and he noticed something peculiar. Whether the lamp was swinging in a wide arc or a narrow one, it seemed to take the same amount of time to complete each swing. Now, that's counterintuitive, right? You'd think a bigger swing would take longer. It covers more distance. But Galileo timed the swings against his own pulse. Because he didn't have a watch, of course. Nobody had a reliable portable timepiece. And he found that the period of the swing, the time for one full back and forth, stayed remarkably consistent, regardless of how wide the arc was. A big swing, a small swing, roughly the same duration. This property is called isochronism, and it's one of those observations that seems simple on the surface, but turns out to be enormously consequential. What Galileo had stumbled upon was the fundamental behavior of a pendulum, that for a given length of string or rod, the period of the swing is essentially constant. Change the length, and the period changes. Make it longer, the swing takes more time. Make it shorter, it swings faster. But for a fixed length, the period stays the same, whether the pendulum is swinging through a wide arc or barely moving at all. At least, that's approximately true for small angles, which is an important qualification we'll come back to. Now, Galileo didn't immediately go build a clock. He was a young man with a lot of other things on his mind. He'd go on to study falling bodies, build telescopes, observe the moons of Jupiter, and get into rather serious trouble with the Catholic Church. But the pendulum stayed with him. He recognized that here was a natural timekeeper, something that beat with a regularity that no mechanical escapement of his era could match. Late in his life, around 1637, when he was old and blind and under house arrest for his astronomical heresies, he dictated designs for a pendulum clock to his son Vincenzo. But Vincenzo never completed it. Galileo died in 1642, and his pendulum clock remained an idea on paper. So the person who actually built the first working pendulum clock was someone else entirely, a Dutch mathematician and astronomer named Christian Huygens. And Huygens is one of those figures in the history of science who deserves to be far more famous than he is. Born in 1629 in The Hague, son of a prominent diplomat and poet, Huygens was brilliant in that wide-ranging way that people in the 17th century could still be. He made fundamental contributions to optics, discovered Titan, Saturn's largest moon, developed a wave theory of light, and in 1656 built the first pendulum clock that actually worked. Here's what Huygens did, and here's why it mattered so much. Remember the Virgin Foliot escapement from those early mechanical clocks? The Foliot, that weighted bar swinging back and forth at the top, had no natural period. Its rhythm depended on how much weight was driving the gear train, how much friction was in the system, how worn the parts were. It was an oscillator, sure, but not a very reliable one. What Huygens realized was that if you replaced the Foliot with a pendulum, you'd have an oscillator with a natural, physics-defined period. The pendulum would swing at its own pace, determined by its length and gravity, and the escapement would simply give it a little nudge each swing to keep it going, while the pendulum in turn regulated how fast the gears could turn. Think of it this way. In the old Virgin Foliot system, the escapement and the oscillator were kind of arguing with each other. The driving weight wanted to spin the gears as fast as possible, and the Foliot was trying to slow it down, and the result was this rough, imprecise compromise. But with a pendulum, the oscillator is the boss. The pendulum says, I swing at this rate, period. And the escapement's job is just to keep it swinging and to count the swings. It's a fundamentally different relationship, and it made clocks dramatically more accurate almost overnight. Huygens's first pendulum clock, built by the clockmaker Salomon Coster in The Hague in 1657, was accurate to about 15 seconds a day. Now, that might not sound incredible to you, living in an age of atomic clocks and GPS satellites. But remember, the best Virgin Foliot clocks were drifting 15 minutes a day. Huygens had just improved timekeeping accuracy by a factor of 60 in one step. That's like going from a car that gets 1 mile per gallon to one that gets 60. It was a revolution. And almost immediately, the implications started rippling outward. Astronomers were ecstatic because they could now time celestial events, eclipses, transits, the movements of Jupiter's moons, with a precision that had been impossible before. Scientists could measure the duration of experiments, and clockmakers across Europe began building pendulum clocks, refining the design, pushing the accuracy even further. One of the key refinements involved the escapement itself. The Verge escapement, even when paired with a pendulum, had a problem. It gave the pendulum a little backward push during part of each cycle, which interfered with its natural swing. So clockmakers developed new escapement designs. The most important was the anchor escapement, which appeared in England in the 1670s, likely invented by Robert Hooke, though the clockmaker William Clement is also credited. The anchor escapement, named because the part that engages with the escape wheel is shaped like a ship's anchor, worked with the pendulum much more gently. It only nudged the pendulum in one direction, and it allowed the pendulum to swing through a much smaller arc, which is important because, remember, the isochronism of a pendulum is most accurate for small swings. A pendulum swinging through a narrow arc of maybe 4 or 5 degrees keeps much more consistent time than one swinging through 30 or 40 degrees. With the anchor escapement and a long pendulum, the kind you see in a grandfather clock, about 1 meter long, which gives you a period of almost exactly 2 seconds, 1 second per swing in each direction. Clocks could now keep time to within about 10 seconds a day. By the early 1700s, the best pendulum clocks were accurate to within a second or two per day. That's astonishing. From 15 minutes of drift to 2 seconds in the span of maybe 70 years. But here's the thing. Pendulum clocks, for all their brilliance, had a fatal flaw when it came to the problem that was killing sailors. They didn't work on ships, and the reason is almost painfully obvious when you think about it. A pendulum needs gravity to work, and it needs to hang freely, and it needs a stable platform. Put a pendulum clock on a ship in the North Atlantic, with the deck pitching and rolling and heaving, and the pendulum goes haywire. It swings wildly. It gets thrown to one side. It stops entirely. Huygens actually tried this. He built marine versions of his pendulum clock in the 1660s and sent them to sea on Dutch vessels. The results were mixed at best and disastrous at worst. The clocks couldn't handle the motion. Other people tried mounting pendulum clocks on gimbals, those pivoting frames that let something stay level while the ship moves around it. And that helped a little, but not nearly enough. The fundamental problem remained. A pendulum is a gravity-driven oscillator, and a ship at sea is a gravity-disrupted environment. So the longitude problem persisted. And it wasn't just an academic puzzle or a minor inconvenience. It was a crisis. In October 1707, a British naval fleet under Admiral Sir Cloudesley Shovel was returning home from the Mediterranean. They thought they were safely west of a chain of rocky islands called the Scilly Isles, off the southwestern tip of England. They were wrong. In fog and darkness, 4 ships struck the rocks. Between 1,500 and 2,000 men drowned, including Shovel himself. It was one of the worst maritime disasters in British naval history, and it was caused, fundamentally, by the inability to determine longitude at sea. That disaster, along with the cumulative toll of centuries of navigational uncertainty, led directly to one of the most famous pieces of legislation in the history of science and technology. In 1714, the British Parliament passed the Longitude Act, which established a board of longitude and offered a series of prizes, the largest being £20,000, an enormous fortune at the time, equivalent to several million pounds today, to anyone who could find a practical method for determining longitude at sea. The method had to be accurate to within half a degree of longitude at the end of a voyage to the West Indies. Half a degree. That meant the timekeeping method, if someone used a clock, would need to be accurate to within about 2 minutes over a voyage of several weeks. 2 minutes of drift, over weeks at sea, on a rolling, pitching, salt-encrusted ship through tropical heat and North Atlantic cold. Every clockmaker in Europe knew this was the prize. And almost every serious scientist and astronomer thought the answer would come not from a clock at all, but from astronomy, from using the positions of the moon and stars to calculate time. The lunar distance method, they called it, and it had powerful champions, including the Astronomer Royal, Neville Maskelyne. The idea that a mechanical clock could ever be made reliable enough for the job struck most of the scientific establishment as, frankly, absurd. And into this world of skepticism and enormous stakes walked a man with no formal education, no university degree, no connections to the scientific elite of London, a carpenter's son from the village of Barrow upon Humber in Lincolnshire, who had taught himself clockmaking by studying every book and mechanism he could get his hands on. His name was John Harrison, and he was about to spend the next 4 decades of his life proving everyone wrong, building a series of marine timekeepers that would push the boundaries of what anyone thought mechanical engineering could achieve. But the path from his workshop in rural England to the deck of a ship crossing the Atlantic was going to be anything but straightforward. Because the establishment didn't just doubt Harrison, they actively worked against him, for decades, in ways that would test any person's sanity and resolve. So let's talk about what Harrison actually built. His first major timekeeper, the one he hoped would win the longitude prize, is known today as H1. He started working on it around 1730, and it took him about 5 years to complete. And when you hear about what went into this machine, you start to understand why people use the word genius when they talk about Harrison, even though he'd probably have been uncomfortable with the term. He was a craftsman. He thought with his hands. H1 is not what you'd picture when someone says clock. It's this extraordinary brass mechanism, about 4 feet tall, weighing around 75 pounds, with 2 interconnected swinging balances linked by brass arcs on top. The whole thing looks more like a scientific instrument from another planet than anything you'd hang on a wall, and every piece of it was designed to solve a specific problem that clocks faced at sea. The linked balances, for instance. Harrison connected them so that as the ship rolled one way, the motion that would throw one balance off would be counteracted by the other balance swinging in the opposite direction. It was a kind of mechanical cancellation. The ship's movement, which destroyed every pendulum clock ever taken to sea, was being neutralized by the geometry of the mechanism itself. But Harrison went further. He knew that temperature changes would wreck accuracy. Metal expands when it's hot and contracts when it's cold, and even tiny changes in the length of a pendulum or the tension of a spring can throw off timekeeping by minutes over a long voyage. So he invented something called the gridiron pendulum, which he'd actually developed years earlier for his land-based clocks. The idea was beautifully simple. You build the pendulum out of alternating rods of 2 different metals, brass and steel, typically, that expand at different rates. You arrange them so that as the brass rods expand downward with heat, the steel rods effectively push the pendulum bob back up by exactly the same amount. The net result? The effective length of the pendulum stays constant regardless of temperature. Think about that. He engineered thermal expansion out of the equation entirely, using nothing but the geometry of 2 different metals. No electronics, no sensors, no feedback systems, just an elegant arrangement of brass and steel that self-corrects. He also tackled friction, which was another clock killer. Most clocks of the era needed regular oiling, and oil was a disaster at sea. It thickened in cold, thinned in heat, attracted dust, and degraded over time. Harrison designed a mechanism using a tropical hardwood called lignum vitae for the bearing surfaces. This wood is so dense and oily that it essentially lubricates itself. A clock that never needs oiling, on a ship in the 18th century. The man was solving problems that most clockmakers hadn't even properly identified yet. Harrison brought H1 to London in 1735 and presented it to the Board of Longitude, the body Parliament had created to administer the prize. He got a trial voyage to Lisbon in 1736, and the clock performed remarkably well. Well enough that on the return voyage, Harrison was able to correct the ship's navigator on their longitude. The navigator had them heading for the wrong landfall, and Harrison's clock said otherwise. Harrison was right. That must have been a satisfying moment. But here's the thing. Harrison himself wasn't satisfied. He knew H1 wasn't accurate enough to win the full prize. He was his own harshest critic. So instead of submitting it for the official trial to the West Indies, he went back to his workshop and started building H2. The Board of Longitude, impressed enough by the Lisbon trial, gave him money to continue his work. And Harrison spent another few years refining, improving, rethinking. H2 was completed around 1741, and it was in many ways a better machine. Same basic concept as H1, with the linked balances, but with improvements to the mechanism throughout. And then, Harrison did something that reveals the depth of his engineering mind. He looked at H2 and realized the entire approach, the big, heavy, linked balance design, had fundamental limitations. The balances were sensitive to the circular motion of a ship in ways he couldn't fully compensate for. so he essentially scrapped the concept and started over. H3 consumed the next 19 years of his life. 19 years. From roughly 1740 to 1759, Harrison worked on this single machine, trying to perfect a large, complex timekeeper that used circular balances instead of the linked bar design. He invented new mechanisms during this period, including a bimetallic strip, two metals fused together that bend predictably with temperature changes, which is a device still used today in thermostats. Every time you hear your heating system click on because the temperature dropped, you're benefiting from something Harrison invented while wrestling with the longitude problem in a workshop in the English countryside. But H3 never fully satisfied him either. And here's where the story takes its most dramatic turn. Sometime in the late 1750s, while still working on H3, Harrison had a revelation. He realized that the answer wasn't a bigger, more complex machine. It was a smaller one, much smaller. He'd been watching the development of pocket watches, and he'd seen a watchmaker named John Jefferies produce a small watch based on some of Harrison's own ideas that kept surprisingly good time. And something clicked. All those years of engineering insight, all those innovations, the temperature compensation, the friction reduction, the escapement designs. What if you packed all of that into something the size of a large pocket watch? The result was H4, and it changed everything. Completed in 1759, H4 looks nothing like its predecessors. Where H1, H2, and H3 were large, heavy, almost sculptural machines, H4 is a watch. A big one, about 5 inches in diameter, but recognizably a watch. It's a beautiful object, with an elaborately engraved case and a white enamel dial. And inside, it contains a concentration of engineering innovation that is staggering for its era. Harrison designed a new escapement, a remontoire mechanism that provided constant force to the balance spring, regardless of variations in the mainspring's power, and temperature compensation using a bimetallic strip. Every component was designed, finished, and adjusted to a level of precision that was essentially unprecedented in watchmaking. In 1761, H4 was sent on its official trial voyage to Jamaica aboard HMS Deptford. Harrison was too old and ill to go himself. He was 68, so his son William went in his place, carrying the watch. The voyage took 81 days. When they arrived in Jamaica and checked the watch against the known longitude of Port Royal, H4 had lost only 5.1 seconds. 5 seconds. Over 81 days at sea. The requirement for the full prize was accuracy to within 2 minutes. Harrison's watch was roughly 23 times more accurate than it needed to be. You'd think that would be the end of the story. Man builds incredible watch. Watch passes the test spectacularly. Man gets the prize. But this is where the human drama gets painful, because the Board of Longitude, heavily influenced by Neville Maskelyne and others who championed the lunar distance method, refused to award Harrison the full prize. They said one trial wasn't enough. They demanded more tests. They changed the rules. They required Harrison to hand over his watches and explain every detail of their construction so that other watchmakers could reproduce them, which Harrison saw, understandably, as giving away his life's work. They awarded him partial payments, grudgingly, but withheld the full £20,000 year after year. There's a particular cruelty in what happened next. Maskelyne, who was both a judge on the Board of Longitude and a direct competitor promoting his own lunar distance method, was put in charge of testing H4 at the Royal Observatory. That's like asking a rival team's coach to referee the championship game. And surprise, under Maskelyne's testing, the watch performed less well than it had at sea. Harrison and his supporters believed the watch was being deliberately mishandled or tested under unfair conditions. Whether or not that's true, the conflict of interest was breathtaking, and it speaks to something important about how engineering progress actually happens in the real world. It's never just about the technology. It's about politics, ego, institutional power, and money. Harrison spent years fighting the board. He was in his 70s, then his 80s, and still battling for recognition. Finally, in 1773, after Harrison petitioned King George III directly, the king himself tested a copy of H4 and found it accurate to within 1/3 of a second per day. Parliament awarded Harrison a payment of £8,750. It wasn't technically the Longitude Prize. The Board of Longitude never officially awarded it to anyone. But it was an acknowledgement, at last, that Harrison had solved the problem. He was 80 years old. He died 3 years later, in 1776. And here's what matters for our story about time. Harrison didn't just solve the longitude problem. He proved that a mechanical device, gears and springs and tiny, precisely shaped pieces of metal, could keep time with an accuracy that the scientific establishment had considered physically impossible. He pushed the boundary of what engineering could do with time from minutes of error per day down to fractions of a second. And in doing so, he opened the door to an entirely new relationship between humanity and precise timekeeping. Because once you can build one Harrison-style chronometer, you can build many. And within a few decades of Harrison's death, marine chronometers based on his principles were being produced in quantity. Navigation transformed. The British Empire's expansion across the globe in the 19th century was built, in a very real sense, on the ability to know exactly where you were at sea. And that ability rested on the work of a self-taught carpenter's son who refused to give up. But accurate mechanical timekeeping, as extraordinary as it was, still had limits. Springs and gears and balance wheels are physical objects, subject to wear, temperature, gravity, and the fundamental messiness of the mechanical world. And as the 19th century gave way to the 20th, as science pushed deeper into the nature of matter itself, people began to wonder whether there might be something more fundamental than a swinging pendulum or an oscillating spring, some natural phenomenon so regular, so constant, that it could serve as the ultimate timekeeper. And the answer, when it came, emerged from one of the strangest and most counterintuitive corners of physics, a place where atoms vibrate at frequencies so precise that they make Harrison's masterpiece look like a sundial in a rainstorm. The story of how we got from mechanical clocks to atomic ones starts, oddly enough, with a Scottish physicist and a set of equations about electromagnetic phenomena that at first glance have absolutely nothing to do with clocks. James Clerk Maxwell, working in the 1860s, managed to unify electricity and magnetism into a single elegant framework. 4 equations that described how electric and magnetic fields interact, how they propagate, how they dance together through empty space as waves traveling at a very specific speed. And that speed, Maxwell realized, was the speed of light, which meant light itself was an electromagnetic wave. Now that's a beautiful piece of physics on its own, but here's why it matters for our story about time. Maxwell's equations revealed that the universe is full of oscillation. Electromagnetic waves are, at their core, things that vibrate, electric fields rising and falling, magnetic fields rising and falling, at frequencies that can range from a few cycles per second all the way up to trillions and trillions of cycles per second. And oscillation, as we've seen again and again in this story, is the heartbeat of every clock ever built. A sundial uses the oscillation of the Earth spinning on its axis. A pendulum clock uses the oscillation of a weight swinging back and forth. Harrison's chronometer uses the oscillation of a balance wheel rocking to and fro. Every clock is just a device that counts oscillations of something. So the question becomes, what oscillates most reliably? What vibrates with the least variation, the least susceptibility to temperature or wear, or the ship rolling beneath your feet? And this is where the story takes a turn into the very small. Because by the early 20th century, physicists were discovering that atoms themselves have natural frequencies of oscillation, specific, precise frequencies at which they absorb and emit electromagnetic radiation. And these frequencies aren't determined by how carefully you machine a gear or how perfectly you shape a spring. They're determined by the fundamental constants of nature, by the charge of an electron, by Planck's constant, by the structure of the atom itself. They're the same everywhere in the universe. Every cesium atom vibrates at exactly the same frequency as every other cesium atom, every hydrogen atom, every rubidium atom. The same, not approximately the same, exactly the same. Think about what that means for a moment. If you could build a clock that counted the vibrations of an atom, you'd have a timekeeper that didn't depend on any human craftsmanship at all. No springs to fatigue, no gears to wear, no oil to thicken in the cold. Just the atom, doing what atoms do, with a regularity set by the laws of physics themselves. The idea was floating around in physics circles for decades before anyone could actually build such a thing. The key theoretical insight came from a technique called magnetic resonance, which was developed in the 1930s and 1940s by a physicist named Isidor Isaac Rabi at Columbia University in New York. Rabi was born in 1898 in what's now Poland, came to the United States as an infant, grew up in Brooklyn, and became one of the great experimental physicists of the 20th century. What Rabi figured out was a way to measure the resonant frequencies of atoms with extraordinary precision. His technique, called the molecular beam magnetic resonance method, worked like this. You send a beam of atoms through a carefully arranged set of magnetic fields, and then you expose them to electromagnetic radiation at a specific frequency. If that frequency matches the natural resonant frequency of the atoms, something measurable happens. The atoms change their quantum state, and you can detect that change. If the frequency is even slightly off, nothing happens. It's like tuning a radio. When you hit exactly the right frequency, you get a clear signal. Miss by even a tiny amount, and you get static. Rabi won the Nobel Prize in Physics in 1944 for this work, and during his Nobel lecture and in interviews afterward, he made a suggestion that must have seemed almost whimsical at the time. He pointed out that this resonance technique could, in principle, be used to build an extraordinarily accurate clock. You'd use the atoms themselves as your frequency standard. Instead of counting the swings of a pendulum, you'd count the vibrations of atoms, locked to their natural resonance frequency by a feedback loop. It was an audacious idea, and it took about a decade for someone to actually make it work. The first operational atomic clock was built in 1955 at the National Physical Laboratory in Teddington, England, by a physicist named Louis Essen and his colleague Jack Parry. Essen was a meticulous experimentalist, the kind of person who'd spent years working on precision measurements of the speed of light using microwave cavity resonators, so he understood both the physics and the engineering of high-frequency electromagnetic oscillation. His clock used cesium atoms, specifically cesium-133, and here's roughly how it worked. You heat up a small oven containing cesium metal, which produces a beam of cesium atoms streaming out into a vacuum chamber. These atoms exist in one of two closely spaced energy states. Think of them as two slightly different configurations of the atom's outermost electron. You use magnets to select only atoms in one particular state, and then you pass them through a cavity where they're exposed to microwave radiation at a very specific frequency, right around 9,192,631,770 cycles per second. If the microwave frequency is exactly right, the atoms flip from one energy state to the other. A detector at the far end of the beam counts how many atoms have flipped. You use that count as a feedback signal. If too few atoms are flipping, your microwave frequency has drifted slightly, so you adjust it. The result is a system that locks itself to the natural resonance frequency of cesium with phenomenal precision. Essen's first cesium clock, called Cesium-1, was accurate to about 1 second in 300 years. Now, that might not sound that impressive compared to what came later, but think about the leap. Harrison's H4, that miraculous 5-inch watch that won the Longitude Prize, lost about 5 seconds over 81 days. Extrapolate that out, and you're looking at maybe 20 seconds of error per year. Essen's clock, in its very first version, was accurate to 1 second in 3 centuries. That's roughly a 5,000-fold improvement in accuracy, achieved not by making better gears or more perfect springs, but by abandoning mechanical oscillation entirely and tapping into the vibrations of nature itself. And here's the thing. Essen's clock was just the beginning. It was a first-generation device, and like Harrison's H1, it was a proof of concept that would be rapidly refined. Within a few years, cesium clocks improved dramatically. By the 1960s, they were accurate to about 1 second in 3,000 years. And in 1967, something remarkable happened. The international scientific community made a decision that fundamentally redefined what a second actually is. Before 1967, the second was defined astronomically. It was a fraction of the mean solar day, or later, a fraction of a specific tropical year. But astronomers had known for a long time that the Earth's rotation isn't perfectly steady. Tidal friction from the moon is gradually slowing the Earth down. Earthquakes can shift mass around and change the rotation rate slightly. The Earth is a messy, complicated physical object, and basing your fundamental unit of time on its behavior is a bit like basing your standard of length on the size of someone's foot. It works, but it's not exactly elegant or stable. So in 1967, the 13th General Conference on Weights and Measures, meeting in Paris, voted to redefine the second. The new definition was breathtakingly specific. 1 second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. That number, 9,192,631,770, wasn't chosen arbitrarily. It was chosen so that the new atomic second would match the old astronomical second as closely as possible. But from that moment on, the second was no longer tied to the heavens. It was tied to the atom, and that's a profound shift. For thousands of years, time had been defined by looking up, at the sun, at the stars, at the rotation of the Earth. Now, for the first time, the fundamental unit of time was defined by looking down into the structure of matter itself. And this redefinition wasn't just a bureaucratic tidbit, it had real consequences. Because once your definition of a second is based on an atomic frequency that's the same everywhere, your clocks can be compared with each other to extraordinary precision. And when you start comparing clocks that carefully, you start to notice things. strange things. Things that force you to grapple with questions that aren't really about engineering at all. They're about the nature of time itself. Here's what I mean. By the 1970s and 1980s, atomic clocks had gotten good enough that physicists could actually test one of the most famous and counterintuitive predictions in all of science, a prediction made by Albert Einstein back in 1905 and 1915 in his theories of special and general relativity. Einstein said that time is not absolute. Time does not flow at the same rate everywhere. A clock that's moving relative to you ticks slower than a clock that's sitting still. A clock that's deeper in a gravitational field, closer to a massive object like the Earth, also ticks slower than a clock that's higher up. These aren't metaphors. These aren't optical illusions. Time itself actually passes at different rates depending on your velocity and your position in a gravitational field. Now, when Einstein first proposed this, it was almost purely theoretical. The effects are incredibly tiny at everyday speeds and everyday differences in altitude. If you live on the ground floor of an apartment building, time passes very, very slightly slower for you than for your neighbor on the top floor. But the difference is so small that no clock in Einstein's era could have detected it. But atomic clocks changed that. In 1971, two physicists named Joseph Haffel and Richard Keating loaded 4 cesium beam atomic clocks onto commercial airliners and flew them around the world, once eastward, once westward. When they compared the flying clocks to reference clocks that had stayed on the ground at the United States Naval Observatory, they found exactly the differences that Einstein's equations predicted. The eastward flying clocks, which were moving faster relative to the Earth's surface, lost about 59 nanoseconds. The westward flying clocks gained about 273 nanoseconds. Nanoseconds, billionths of a second. Tiny, tiny differences, but real, measurable, exactly as predicted by a theory written down more than half a century earlier by a patent clerk in Bern. And this is where timekeeping stops being just an engineering problem and starts being something deeper, something almost philosophical. Because if time itself flows at different rates in different places, then what does it even mean to say that two events happened at the same time? What does simultaneity mean in a universe where your clock and my clock can disagree? Not because one of them is broken, but because time itself is genuinely passing at different rates for each of us. This isn't an abstract puzzle. It has brutally practical consequences. And the most vivid example is one you probably interact with every single day without thinking about it: the Global Positioning System. GPS. The system that tells your phone where you are, that guides airplanes to runways, that lets you navigate to a restaurant you've never been to before. GPS works by triangulation, using signals from a constellation of satellites orbiting the Earth at an altitude of about 20,200 kilometers. Each satellite carries an atomic clock, and it continuously broadcasts a signal that says, essentially, I am satellite number such and such, and the time right now is this. Your GPS receiver picks up signals from multiple satellites, notes the tiny differences in arrival time, and uses those differences to calculate your position. The whole system depends on knowing the time on each satellite to within about 20 to 30 nanoseconds. If the clocks are off by more than that, your position calculation starts to drift. And it drifts fast, by roughly 10 meters, for every 30 nanoseconds of clock error. Here's the kicker. Those satellites are moving at about 14,000 kilometers per hour relative to the ground, which means special relativity causes their clocks to tick slower by about 7 microseconds per day. But they're also 20,200 kilometers above the Earth, where gravity is weaker, which means general relativity causes their clocks to tick faster by about 45 microseconds per day. The net effect is that the satellite clocks run about 38 microseconds per day faster than clocks on the ground. 38 microseconds. That sounds like nothing. But if you didn't correct for it, the position errors would accumulate at a rate of about 10 kilometers per day. Within a week, your GPS would be telling you you're in a different city. So every GPS satellite has its clock rate deliberately adjusted before launch, slowed down slightly so that once it's in orbit, the relativistic effects bring it into sync with ground-based time. Einstein's theory of relativity, born from thought experiments about trains and lightning bolts, is literally programmed into the satellites orbiting above your head right now. Without it, the navigation system that modern civilization depends on would be useless within a day. And that's not just a neat physics demonstration. That's the world you live in. Every time you open a map on your phone, every time a plane descends on an instrument approach through fog, every time an ambulance dispatcher routes the nearest unit to your street, every time a farmer uses precision agriculture to plant seeds within centimeters of where they should go. All of it rests on clocks so accurate that the curvature of space-time itself becomes a practical engineering problem. That's where timekeeping has taken us, from sundials casting shadows on temple floors to correcting for the warping of the universe. And honestly, that trajectory alone would be enough to make this one of the great stories of human ingenuity. But here's the thing. It doesn't stop there. Because once you have atomic clocks that are good enough to reveal relativistic effects, the natural question becomes, can we make them even better? And the answer, as it turns out, is spectacularly yes. Let's talk about what happened after cesium. Remember, the original cesium standard that Essen and Perry built in 1955 was accurate to about 1 second in 300 years. That was revolutionary. But by the 1990s and into the 2000s, the best cesium fountain, clocks, a refined version of the concept where you toss cesium atoms upward in a fountain-like arc to give them more interaction time with the microwave field. Those clocks had pushed accuracy to about 1 second in 100 million years. That's an improvement of roughly 300,000 times over Essen's original, and it happened within about half a century. But even that wasn't the frontier anymore, because physicists had realized that microwaves, the frequency band cesium operates in, aren't actually the ideal part of the electromagnetic spectrum for building the most precise clocks. Optical frequencies, visible light and near visible light, oscillate far, far faster. Cesium's hyperfine transition ticks at about 9.2 billion times per second, which sounds fast, and it is. But an optical transition in something like a strontium atom ticks at around 429 trillion times per second. That's roughly 50,000 times faster. And here's why that matters. The faster your pendulum swings, the more precisely you can slice up a second. It's the same principle that made Huygens's pendulum clock better than the old Virgin Foliot. More ticks per second means finer resolution, means better accuracy. So if you could build a clock that uses an optical frequency instead of a microwave frequency, you'd have something fundamentally more precise. The problem, for decades, was that nobody could actually count optical frequencies. Microwaves, sure. Electronic circuits can keep up with billions of oscillations per second. But trillions? That was beyond any electronics. You'd be like someone trying to count the individual vibrations of a guitar string by watching it with your eyes. Way too fast. You need some kind of bridge between the optical frequency you want to use and the electronic frequencies you can actually measure. And that bridge arrived in the year 2000 with a device called the optical frequency comb. This is one of those inventions that sounds almost too elegant to be real. The key figure here is Theodor Hensch, a German physicist working at the Max Planck Institute in Garching, along with John Hall at Gila in Boulder, Colorado. They shared the Nobel Prize in Physics in 2005 for this work, and it's one of those Nobel Prizes that was completely deserved because the frequency comb changed everything. Here's how it works, roughly. You take a special kind of laser called a mode-locked femtosecond laser, a laser that emits extremely short pulses of light, each one lasting just a few quadrillionths of a second. When you look at the spectrum of this pulsed laser, something beautiful happens. Instead of a single frequency, it produces a whole series of evenly spaced frequencies, like the teeth of a comb. Hence the name. Each tooth corresponds to a precise harmonic of the laser's pulse repetition rate, and that repetition rate is something you can measure with electronics. It's typically in the range of hundreds of millions of hertz, which is well within the reach of conventional counters. So now you have this comb of optical frequencies, each one precisely known, stretching across a huge swath of the spectrum. If you want to measure the frequency of some atomic transition way up in the optical range, you just compare it to the nearest tooth of the comb. The comb acts as a ruler for light. A frequency ruler with hundreds of thousands of perfectly spaced markings, connecting the countable world of electronics to the uncountable world of optical oscillations. It's like building a ladder from the ground floor all the way up to the top of a skyscraper, rung by rung, each rung exactly the same distance apart. With the frequency comb in hand, optical clocks suddenly became possible, and the race was on. Different labs around the world started building clocks based on different atoms and ions, each one chosen for having a particularly narrow, stable optical transition. There are strontium lattice clocks, where thousands of strontium atoms are trapped in a grid made of intersecting laser beams, an optical lattice, and interrogated simultaneously. There are aluminum ion clocks, where a single aluminum ion is held in an electromagnetic trap, and its quantum state is read out through a partner beryllium ion. There are ytterbium clocks, lutetium clocks, each one pushing the boundaries in slightly different ways. And the accuracies these things achieve are genuinely hard to wrap your mind around. The best optical clocks today, as of the early 2020s, are accurate to about 1 second in 15 to 30 billion years. Let that land for a moment. The universe is about 13.8 billion years old. These clocks would not have gained or lost a single second since the Big Bang. In fact, they'd still be on time if the universe were twice its current age. That's not an incremental improvement over cesium. That's a leap of several orders of magnitude, and it means these clocks are now so sensitive that they can detect the gravitational time dilation caused by lifting the clock just 1 centimeter higher in Earth's gravitational field. 1 centimeter. Einstein's general relativity tells us that a clock 1 centimeter higher ticks very, very slightly faster because gravity is infinitesimally weaker there. And modern optical clocks can actually see that difference. They've become gravity sensors, in a way. Tools for measuring the shape of Earth's gravitational field with extraordinary precision. A discipline called relativistic geodesy, which sounds like science fiction but is becoming a real, practical field. Think about what that means. You could, in principle, use a network of optical clocks to map the geoid, the shape of Earth's gravitational equipotential surface, more precisely than any satellite mission has managed. You could detect underground density changes, maybe even monitor volcanic activity or shifting water tables, just by watching how clocks at different locations drift relative to each other. Time becomes a way of sensing the Earth itself, and this connects to something bigger that's been quietly happening in the background of all this precision timekeeping: the redefinition of the second. Remember, the current definition of the second has been tied to cesium since 1967. That's over half a century now, and optical clocks have surpassed cesium clocks by such a wide margin that the definition is, in a sense, holding back the state of the art. It's like having a ruler that's accurate to a millimeter when you have tools that can measure in nanometers. The ruler becomes the limitation. So there's been a slow, careful, international process underway, coordinated through the Bureau International des Poids et Mesures, the BIPM, in Paris, to eventually redefine the second based on an optical transition. The leading candidates include strontium-87 and ytterbium-171, both of which have been extensively studied and compared across labs on different continents. The target date has shifted a few times, but the metrology community has been working toward a redefinition sometime in the late 2020s or early 2030s. And if you think about it, this will be only the third fundamental change in how humanity defines the second. First, it was based on the rotation of the Earth, 186,400th of a mean solar day. Then, in 1967, it was redefined in terms of cesium, and soon it'll be redefined again in terms of an optical transition. Each time the definition gets more precise, more universal, more divorced from the parochial accidents of our particular planet. The rotation of the Earth is irregular, influenced by tides and earthquakes and the slow redistribution of mass in the mantle. Cesium gave us something far more stable. Optical clocks give us something more stable still, and each redefinition ripples outward through every system that depends on precise time. But here's something that might surprise you. Even as clocks have gotten almost incomprehensibly precise, we've also had to grapple with a strange, practical problem: keeping the world's official time in sync with the sloppy, irregular, gradually slowing rotation of the Earth. Because civil time, the time on your clock, the time zones you live in, still needs to roughly correspond to the position of the sun in the sky. Noon should still feel like the middle of the day. And that creates a tension, because atomic time marches forward with perfect regularity, while the Earth's rotation is anything but regular. The Earth is gradually slowing down, mostly due to tidal friction from the Moon, losing about 2.3 milliseconds per century on average, which means that a day defined by the Earth's rotation is getting imperceptibly longer, while the atomic second stays fixed. The solution, since 1972, has been the leap second. You've probably heard of these without knowing quite what they are. Every so often, roughly every year to 18 months, though the interval varies, the International Earth Rotation and Reference System Service, based in Paris, announces that a leap second will be inserted into Coordinated Universal Time, UTC. At midnight on the designated date, usually June 30th or December 31st, the clock reads 23:59:59, then 23:59:60, then 0:00:00:0. An extra second slipped in to keep atomic time aligned with the Earth's rotation to within 0.9 seconds. It's a strange little hack when you think about it. The most precise timekeeping system ever devised, periodically nudged by a full second to accommodate the messy, unpredictable wobble of a spinning rock. And leap seconds have caused real problems. In 2012, a leap second insertion, caused widespread issues with Linux servers, crashing Reddit, disrupting Qantas airline booking systems, and causing glitches at Mozilla. The problem is that most software isn't written to handle a minute with 61 seconds. It sounds trivial, but when your entire digital infrastructure assumes that time moves in predictable, uniform increments, even a single unexpected second can cascade into chaos. Financial trading systems, telecommunications networks, power grids, all of them have had to develop special protocols for handling leap seconds, and not all of them get it right every time. Which is why, in November 2022, the General Conference on Weights and Measures, the same body that redefined the second in 1967, voted to abolish leap seconds by 2035. The plan is to let the difference between atomic time and solar time gradually accumulate, and to deal with it through some larger, less frequent adjustment, perhaps a leap minute far in the future, or some other mechanism that hasn't been fully decided yet. It's a remarkable moment if you think about it. For the first time, the international community has decided that the precision and uniformity of atomic time matters more than keeping clocks perfectly aligned with the sun. The sun, which was the original clock, the thing that defined time for every human civilization that ever existed, is being gently but firmly demoted. Time is no longer what the earth says it is. Time is what atoms say it is. And that philosophical shift connects to something even deeper, something that physicists have been wrestling with for over a century now, which is the question of what time actually is at the most fundamental level. Because so far, everything we've talked about, sundials, pendulums, cesium atoms, optical lattices, these are all ways of measuring time. They're clocks. But a clock measures time the way a thermometer measures temperature. The instrument isn't the thing itself. So what is the thing itself? What is time, really, when you strip away all the instruments? This is where physics gets genuinely strange, and where the story of timekeeping intersects with some of the deepest questions in science. And it starts, as so many things in modern physics do, with a puzzle that Einstein noticed. Or rather, a puzzle that Einstein noticed before almost anyone else thought to ask it. And the puzzle was this: what does it mean for two things to happen at the same time? That sounds like a trivial question, right? If two firecrackers go off at the same time, they go off at the same time. What's to puzzle over? But Einstein, who was 26 years old in 1905 and working as a patent clerk in Bern, Switzerland, not a professor, not at a fancy research lab, just a guy reviewing patent applications for electromagnetic devices, he realized that at the same time is not as simple as it sounds the moment you take seriously the fact that information travels at a finite speed. Light is fast, extraordinarily fast, about 300 million meters per second, but it is not infinitely fast, and that matters more than you might think. Here's the thought experiment Einstein used, more or less. Imagine you're standing exactly midway between two trees, and lightning strikes both trees at the same instant. You see both flashes arrive at your eyes simultaneously, and you say, "Those two strikes happened at the same time." Fair enough, but now imagine someone else is on a train moving very fast from one tree toward the other. They're passing through the midpoint at the exact moment the lightning strikes. Because they're moving toward one tree and away from the other, the light from the tree they're approaching reaches them a tiny bit sooner than the light from the tree they're moving away from. So from their perspective, the two strikes did not happen at the same time. One happened first. Now, your instinct, and honestly, everyone's instinct, is to say, well, sure. But really, they happened at the same time. The person on the train is just seeing them wrong because they're moving. But here's the thing Einstein understood. There is no experiment you can do, no measurement you can make, that privileges one observer over the other. The person on the train has just as much right to call themselves stationary and say you're the one who's moving. The laws of physics work exactly the same way for both of you. There is no cosmic referee who can say which one of you is right about what happened first. And if two equally valid observers disagree about whether two events are simultaneous, then simultaneity, the idea of at the same time, is not an absolute fact about the universe. It depends on who's asking. It depends on how you're moving. That was Special Relativity, published in June 1905, and it absolutely shattered the idea of universal time. Before Einstein, everyone assumed, Newton certainly assumed, that there was one single clock ticking away for the whole universe, and every event had a definite, absolute time coordinate that everyone would agree on. Time was like a river flowing at the same rate everywhere, carrying everything forward together. Einstein showed that's not how it works. Time is more like, well, imagine each observer carrying their own personal clock, and those clocks don't necessarily agree. Not because the clocks are broken, but because time itself passes at different rates depending on how you're moving. This is time dilation, and it's not a metaphor. It's not a trick of perception. Time genuinely, physically, passes more slowly for objects moving at high speeds relative to you. If your twin got on a spaceship and flew to a nearby star at 90% the speed of light and came back, they would be measurably younger than you when they returned. Not because the trip felt shorter to them, though it would, but because less time actually elapsed for them. Their heart beat fewer times, their cells divided fewer times, their clock, any clock, mechanical, atomic, biological, ticked fewer times. This is the famous twin paradox, and it's been confirmed experimentally so many times now that it's really not a paradox at all. It's just how the universe works. Remember Haffele and Keating flying atomic clocks around the world on commercial airliners back in 1971. That was a direct measurement of this effect. The clocks that flew came back showing less elapsed time than the ones that stayed home by exactly the amount relativity predicted. But special relativity was only half the story. Einstein spent the next 10 years from 1905 to 1915 working on the harder problem. What happens when you include gravity? And the result, general relativity, is where things get truly mind-bending for our understanding of time. Because what Einstein showed is that gravity also affects the passage of time. The stronger the gravitational field you're sitting in, the more slowly time passes for you compared to someone in weaker gravity. A clock on the ground floor of a building ticks slightly more slowly than a clock on the top floor, because the ground floor is closer to the center of the Earth and therefore in a slightly stronger gravitational field. The difference is absurdly small. We're talking nanoseconds over years for the height of a building. But it's real, and modern clocks can measure it easily. Those optical lattice clocks we were talking about, the ones accurate to 1 second in 15 billion years, they can detect the gravitational time dilation caused by lifting the clock just 1 centimeter higher. 1 centimeter. That's the thickness of your little finger, and it creates a measurable difference in the flow of time. So here's where we are. Time is not universal. Time is not absolute. Time passes at different rates depending on how fast you're moving and how deep you are in a gravitational field. Every point in space has its own local rate of time, and those rates are all slightly different. The GPS satellites we talked about earlier, the ones that need atomic clocks to tell you where your car is, they have to account for both of these effects simultaneously. The satellites are moving fast relative to you, which makes their clocks tick slower by about 7 microseconds per day due to special relativity, but they're also higher up, in weaker gravity, which makes their clocks tick faster by about 45 microseconds per day due to general relativity. The two effects partially cancel, but the gravitational effect wins, so the net result is that the satellite clocks run about 38 microseconds per day faster than ground clocks. And if you didn't correct for that, your GPS position would drift by roughly 10 kilometers per day. So every time you use your phone to navigate to a restaurant, you are relying on Einstein being right about the nature of time, which he was. Now, general relativity doesn't just say that gravity slows down time. It says something much more radical. It says that gravity is the curvature of space-time. Mass and energy warp the fabric of space and time around them, and what we experience as gravity is just objects following the natural curves of that warped geometry. The Earth doesn't pull you down through some invisible force reaching across empty space. Rather, the Earth's mass bends space-time in its vicinity, and the path your body naturally follows through that curved space-time happens to lead toward the Earth's center. Time dilation near massive objects isn't a side effect of gravity. In a very real sense, it is gravity. The slowing of time near mass is part of what creates the curvature that we experience as gravitational attraction. Think about what that means for a second. Time isn't just something that happens inside the universe, like a backdrop against which events play out. Time is part of the structure of the universe. It bends, it stretches. It's woven into the same geometric fabric as space. When a massive star collapses into a black hole, the curvature of space-time becomes so extreme that time, as experienced by someone falling in, slows down more and more relative to a distant observer. At the event horizon, the boundary of the black hole, from the outside perspective, time appears to stop completely. The infalling person never quite seems to cross the boundary. They just get dimmer and redder and slower, frozen at the edge of the hole forever. From their own perspective, of course, they sail right through. Their local time keeps ticking normally. They don't feel anything special at the horizon. But the time that has elapsed for them, and the time that has elapsed for the distant observer, have diverged so dramatically that they're essentially living in different temporal realities. This is not science fiction. We have observational evidence for extreme gravitational time dilation near black holes. The Event Horizon Telescope collaboration, which produced that famous image of the black hole shadow in the galaxy M87 in 2019, was observing matter orbiting so close to a black hole that time dilation is a significant factor in the physics of what's happening there, and gravitational wave detectors like LIGO, which first detected ripples in space-time from merging black holes in September 2015, are literally measuring the stretching and squeezing of space and time itself. The signals they detect, tiny oscillations in the length of their 4-kilometer laser arms, oscillations smaller than 1,000th the width of a proton, are the signature of space-time ringing like a bell after two black holes spiral into each other. Time, in those cataclysmic moments, is doing things that would have been completely unimaginable to the people building sundials in Egypt or water clocks in Babylon. And yet, even general relativity, as profound and successful as it is, doesn't give us the final answer about what time really is. Because there's another great theory of physics, quantum mechanics, and its relationship with time is deeply strange, and, honestly, unresolved. In quantum mechanics, time plays a peculiar role. Every other physical quantity, position, momentum, energy, spin, is represented by a mathematical object called an operator, something that can have a spread of possible values, something subject to uncertainty. But time in quantum mechanics is not an operator. It's a parameter. It's the background variable, the thing you plug in to tell the equations when to evaluate everything else. Time in quantum mechanics is more like Newton's absolute time than like Einstein's flexible, warping space-time. It just ticks along, unchanged, providing the stage on which quantum events unfold. This mismatch, general relativity says, time is dynamic, flexible, part of the geometry of the universe. Quantum mechanics treats time as fixed, external, absolute, is one of the deepest unsolved problems in all of physics. It's at the heart of why we don't yet have a complete theory of quantum gravity, a framework that unifies general relativity with quantum mechanics. People have been working on this for decades. String theory, loop quantum gravity, causal set theory. These are all attempts to build that unified framework, and they all have to grapple with the question of what time is at the most fundamental level. Some approaches suggest that time might be emergent, meaning it doesn't exist at the most basic level of reality, but arises from something deeper, the way temperature arises from the collective motion of molecules. In that view, asking, "What is time really?" might be like asking, "What is temperature really?" at the level of individual atoms. The question sort of dissolves, because the concept only makes sense at a higher level of description. There's a beautiful and somewhat haunting equation in quantum gravity called the Wheeler-DeWitt equation, written down by John Wheeler and Bryce DeWitt in the 1960s. It's meant to describe the quantum state of the entire universe. And here's what's strange about it. Time doesn't appear in it at all. The equation is timeless. It describes a static quantum state, and yet somehow our experience of time, of change, of one moment following another, of clocks ticking and stars burning and people growing old, is supposed to emerge from it. How? Nobody knows for certain. There are proposals. One idea, associated with Don Page and William Wooters in the 1980s, suggests that time emerges from quantum entanglement between different parts of the universe. If you're inside the universe, you can use one part as a clock to measure change in another part, and that relational change is what you experience as time. But from outside, if such a perspective even makes sense, nothing is changing at all. It's the kind of idea that can make your head spin if you think about it too hard, which is maybe not what you want right now, lying there in the dark. So let's bring it back down to something more tangible, something you can almost feel, because there's one more aspect of time that physics has struggled with, one that's arguably the most familiar and the most mysterious of all, and that's the fact that time seems to have a direction. The past is different from the future. You remember yesterday, but not tomorrow. Eggs break, but don't unbreak. Coffee cools, but doesn't spontaneously heat up. We call this the arrow of time, and explaining why it exists turns out to be surprisingly difficult, because almost all the fundamental laws of physics, Newton's laws, Maxwell's equations, Einstein's field equations, even the Schrödinger equation of quantum mechanics, are time-symmetric. They work exactly the same whether you run them forward or backward. If you filmed a billiard ball bouncing around a table and played the film in reverse, the reversed version would obey Newton's laws perfectly. Nothing would look wrong. So if the laws of physics don't care which direction time goes, why does the universe so obviously seem to have one? Why does the universe so obviously move in one direction? From past to future, from order to disorder, from eggs intact to eggs scrambled on the kitchen floor? The answer, or at least the best answer anyone has come up with, lives in thermodynamics. Specifically, it lives in the second law of thermodynamics, which says that the entropy of a closed system tends to increase over time. Entropy, you've probably heard the word before, may be associated with disorder or randomness, and that's roughly right, though the precise meaning is a bit subtler. Entropy is really a measure of how many different microscopic arrangements of a system are consistent with its macroscopic appearance. A neatly stacked deck of cards, sorted by suit and number, has low entropy. There's basically one arrangement that looks like that. A shuffled deck has high entropy. There are astronomically many arrangements that all look equally random. And the second law says that systems naturally evolve from low entropy states to high entropy states, simply because there are so many more high entropy states to land in. It's not that the laws of physics push you toward disorder. It's that disorder is overwhelmingly more probable. If you shuffle a sorted deck, you'll almost certainly end up with a messy one, not because shuffling prefers messiness, but because almost every possible arrangement is messy. And here's the thing. That's it. That's the arrow of time. The reason eggs break and don't unbreak, the reason coffee cools and doesn't spontaneously heat up, the reason you remember the past and not the future, is that the universe is moving from a state of lower entropy to a state of higher entropy. The second law gives time its direction. Without it, the fundamental laws of physics would be perfectly content to run backward. With it, there's a clear before and after. But now you have to ask the obvious follow-up question, the one that the Austrian physicist Ludwig Boltzmann wrestled with in the late 1800s, the one that still haunts physicists today. If entropy naturally increases, if systems naturally move toward their most probable state, then why was entropy ever low in the first place? If the universe tends toward maximum disorder, how did it start in such an extraordinarily ordered state? Because that's what the evidence tells us. The early universe, right after the Big Bang roughly 13.8 billion years ago, was in a state of astonishingly low entropy. Matter and energy were distributed with remarkable uniformity. The cosmic microwave background radiation, that faint afterglow of the Big Bang that we can still detect today, is uniform to about 1 part in 100,000. That smoothness, that uniformity, represents an incredibly special, incredibly low entropy gravitational state. And everything that has happened since, the formation of galaxies, stars, planets, the chemistry that led to life, the cup of coffee cooling on your nightstand, all of it is just entropy increasing, the universe rolling downhill from that improbable starting point. This idea, that the arrow of time ultimately traces back to the special initial conditions of the universe, is sometimes called the past hypothesis. The philosopher David Albert gave it that name, though the idea goes back much further, at least to Boltzmann, and arguably to the origins of statistical mechanics itself. The past hypothesis simply states that the universe began in an extremely low entropy state. It doesn't explain why. It just says that it did, and that this initial condition, combined with the second law, is what gives rise to everything we experience as the flow of time. And if you're lying there thinking, wait, that's not really an explanation, that's just pushing the question back one step, you're absolutely right. It is. Why did the universe start with low entropy? That's one of the deepest unsolved problems in physics. Some cosmologists think the answer might lie in the dynamics of the Big Bang itself, perhaps the process that created our universe naturally produces low entropy initial conditions. Others, like Roger Penrose, have proposed specific hypotheses. Penrose suggested something he calls the Weyl curvature hypothesis, the idea that gravitational degrees of freedom were somehow constrained to be very smooth at the beginning of time, even though matter was hot and dense. He's spent decades working on this, and it connects to his broader cosmological model called conformal cyclic cosmology, where the universe goes through infinite cycles, each one beginning in a low entropy state. It's speculative, it's beautiful, and it's the kind of idea that only someone who spent a lifetime thinking about the geometry of spacetime could come up with. But let's step back from the edge of the unknown for a moment and appreciate what we do understand, because it's actually quite remarkable. We started this whole journey, you might remember, with ancient Egyptians watching the sun move across the sky, dividing daylight into 12 parts, driving sticks into the ground to track shadows. That was timekeeping at its most human, most intuitive. Time was just what happened between sunrise and sunset. And then the Babylonians gave us base 60, which is why you have 60 seconds in a minute and 60 minutes in an hour, a choice made thousands of years ago by people writing in cuneiform on clay tablets, a choice that stuck. Medieval monks needed to pray at specific hours and drove the development of mechanical clocks, which spread across Europe and changed the way entire societies organized themselves. Galileo watched a chandelier swing in a cathedral and noticed something about pendulums that Christian Huygens turned into the most accurate timekeeping device the world had ever seen. And then the problem of longitude, ships lost at sea, thousands of sailors dead, an empire desperate for a solution, led a self-taught carpenter from Yorkshire named John Harrison to spend decades of his life building clocks that could survive the pitch and roll of the ocean. His H4, that beautiful pocket watch-sized masterpiece, proved that mechanical precision could solve one of the great practical problems of the age. Think about the arc of that story. From sundials to a device that could keep time to within a few seconds across a 2-month Atlantic voyage. That's extraordinary. But even Harrison's clocks, magnificent as they were, measured time by counting the oscillations of a physical mechanism, a spring, a balance wheel, something moving back and forth. The 20th century changed that completely. Isidore Rabi's molecular beam resonance work in the 1930s and 1940s opened the door to using atoms themselves as timekeepers. And by 1955, Louis Essen and Jack Parry at the National Physical Laboratory in England had built a clock that kept time by counting the vibrations of cesium atoms, 9,192,631,770 oscillations per second, a number that in 1967 became the literal definition of the second. Not the rotation of the Earth, not the orbit around the sun, but the behavior of a cesium atom. Time had been redefined in terms of the fundamental properties of matter, and then even that wasn't enough. The frequency combs developed by Theodore Hensch and John Hall, that Nobel Prize-winning work in 2005, let us bridge the gap between microwave frequencies and optical frequencies, and suddenly we could build clocks that tick hundreds of trillions of times per second, clocks based on strontium or aluminum or ytterbium atoms, clocks so accurate they won't gain or lose a second in 15 billion years, longer than the current age of the universe. Clocks so sensitive they can detect the difference in the flow of time between your head and your feet, because your feet are closer to the Earth and time runs just slightly slower down there, exactly as Einstein predicted. Which brings us to Einstein, who showed us that time isn't what we thought it was at all. It's not a fixed background, not a universal stage on which events play out. It's woven into the fabric of the universe itself. It stretches and compresses depending on how fast you're moving and how deep you are in a gravitational field. And two events that are simultaneous for one observer might not be simultaneous for another. Time is personal. Time is local. And yet, somehow, out of all that relativity and all that quantum strangeness, out of the Wheeler-DeWitt equation, where time disappears entirely, and entanglement-based proposals where it emerges from the relationships between quantum systems, out of all of that, we still experience time the way we always have. One moment follows another. The coffee cools. The night deepens. There's something almost comforting about the fact that after all this, after atomic clocks and general relativity, and the past hypothesis and the arrow of time, the most fundamental questions remain open. Why did the universe begin in a low entropy state? Is time truly fundamental, or does it emerge from something deeper? Will quantum gravity, whenever we figure it out, reveal that time at the Planck scale is nothing like what we experience? These are questions that the smartest people alive are working on right now, and they don't have the answers yet. And that's okay. That's actually kind of wonderful. It means the story isn't over. But here's what we do know, and it's worth holding on to as you lie there. We know that human beings have been trying to understand time for as long as there have been human beings. We know that every civilization, every culture, has looked at the sky and tried to make sense of the rhythm of days and seasons and years. We know that this urge to measure, to count, to pin down the flow of moments, it's driven some of the most remarkable engineering achievements in history, from the water clocks of ancient Egypt to the optical lattice clocks in laboratories today that can measure the curvature of space-time with centimeter precision. We know that the quest for better clocks has repeatedly transformed the world in ways that the clockmakers themselves never imagined, enabling navigation, then telecommunications, then GPS, then the entire infrastructure of modern digital life. All of it synchronized, all of it depending on our ability to count the oscillations of atoms with extraordinary precision. And we know that time, for all its strangeness, for all the ways that physics has revealed it to be far more flexible and far more mysterious than our everyday experience suggests, still does what it has always done. It carries you forward. One breath, then another. One heartbeat, then the next. The night moves on, the way nights do, and you move with it, the way you always have, without needing to understand exactly how or why. The clocks in your house are ticking, or humming, or silently counting oscillations in a quartz crystal somewhere inside their circuits. The cesium atoms in the atomic clocks at standards laboratories around the world are vibrating at their steady 9.2 billion cycles per second, defining the second, anchoring the global timescale that keeps everything synchronized. Somewhere, in a quiet lab, an optical clock is counting even faster, hundreds of trillions of ticks per second, measuring time with a precision that would have been literally unimaginable to Harrison, to Huygens, to Galileo, to the nameless Egyptian who first drove a stick into the sand and watched its shadow move. And out there, beyond all of it, the universe is doing what it's been doing for 13.8 billion years, expanding, cooling, increasing in entropy, moving along the arrow of time that began with whatever extraordinary event set the whole thing in motion. The same arrow of time that makes your eyelids heavy, that makes the night feel like it's deepening around you, that makes sleep feel like the most natural thing in the world right now. So let it come. You don't need to keep track of the seconds. You don't need to count the oscillations. The clocks will do that for you. They always have in one form or another for thousands of years. All you need to do is let go, the way a pendulum eventually comes to rest, the way the coffee cools to room temperature, the way everything in the universe gently, inevitably, settles toward equilibrium. That's not a sad thing. That's just time doing what time does. And right now, what time is doing is carrying you softly, quietly, into sleep.